Hi, everybody. This is a mini lecture on correlation and regression. Excuse me. So I think that you are mostly familiar with correlations and had some introduction to simple linear regression. Simple linear regression just means you have one predictor variable and one dependent variable or outcome variable. So I'm just going to talk a little bit about what correlation is and then how it's related to simple linear regression. So what correlation is? First, it is the average association between two variables. And for the most part, the variables need to be measured on an interval ratio scale. So if you look at the formula for how you calculate correlation coefficient, which you can find in chapter 12, each pair of scores. So say you have 10 cases in your data set, and each case has scores on two variables. The correlation is between how much each pair of scores on these two variables are similar to each other on average. So as scores on one of the variables go up, do scores on the other variable go up on average or down on average, or is there no relationship between the two? So that's what a correlation coefficient tells you. It tells you the strength of the association between the two variables, and it does this with a range of scores ranging from -1 up to +1. Numbers in the negative direction are equally strong as numbers in the positive direction. So the direction doesn't tell you about the strength. The direction tells you whether, as scores on one variable go up, the scores on the other variable go up or down on average. So if the two variables, scores on the two variables move in the same direction, it's a positive correlation. And if they move in opposite direction, it's a negative correlation. So for example, if the amount of time that you spend studying is associated with your score on the test, you would assume that there's a positive correlation there, that the more you study, the higher your score is on the test. Now, the reason that it's important to remember that it's an average is that this isn't going to be the case for everybody. There's going to be some students who don't study at all and get a really high score. There's going to be some students who study a lot and get a really low score. But on average, the more students study, the higher their score on the test is. That will be a positive correlation. The number of hours of sleep somebody gets and their score on the test might be negative, my bad, that would be positive too. How about the number of drinks somebody has the night before the test and their score on the test? That might be negative. The more you drank, the lower your score would be on the test, on average. Not for everybody. Some people can go out and have a wild time and still do great on the test, but on average, the more drinks you have, the lower your test score will be. That would be a negative correlation. As you've heard time and time again, I'm sure, correlation does not mean causation. Just because two variables are correlated, it doesn't mean that one variable is causing the other. Now, it doesn't mean that they're not. In fact, you can't have a causal relationship without a correlation, but just having the correlation doesn't mean you've got causation. And the correlation involves standardized variables. So as we get into regression, you'll see there's an unstandardized regression coefficient and a standardized regression coefficient known as the beta. When you've got one predictor variable and one outcome variable, the standardized regression coefficient is the exact same thing as the correlation coefficient because they're both standardized. Remember in 51, you found standard scores by finding one score, like minus the mean divided by the standard deviation. That's standardization. So how are correlation and regression related? As I mentioned, in simple linear regression, correlation and regression are basically the same thing. The correlation coefficient tells you how strongly two variables are related to each other and in what direction, which is useful. The regression coefficient just uses the correlation to find actual predicted values of one variable for each value of the other variable. So if I know somebody is 5 feet 6 inches tall, I could predict their weight to be blank. That would be an example. Now, how good these predictions are, the quality of these predictions, the accuracy of the predictions in a regression coefficient, depends on the strength of the correlation coefficient. When the two variables are really strongly correlated, then I know if I know somebody's weight, I can predict their height pretty accurately. But if those two variables are not strongly correlated, then my predictions will not be very accurate. And the thing that shows sort of the quality of the predictions is the regression line and where it goes through a scatter plot. So I'm going to show you what that looks like now. Switch over to this real quick. Okay, so here I've got 10 cases. These are made up. And here I've got their height in inches, and here I have their weight in pounds. Now look what I can do. I can add a graph. And this is a scatter plot where it shows for each case, this is their height and their weight data. So the one case was 62 inches tall. They weighed this much, which looks like about 180. This person was 64 inches tall. They weighed about 225. This person was 66 inches tall, and they weighed here about 140 or 135. Now look, we don't have like a clear pattern here. This person, even though they're shorter, weighs more than this person. This person, who's taller, weighs more than this person and this person, but this person is shorter than this person. So it's not going in a constant direction. And if we add a regression line in here, you can see just how bad our predictions are. See this line right here? Let me make this a little easier to see. Make it, how about red? Okay, that didn't do anything. So, see this regression line going here, it's a good predictor of this case, and this case, and this case, but you see how it's an awful predictor of this case, and not very good for this case, these cases, or this case. This regression line is almost flat. It shows a very weak positive correlation. And if you look at the correlation that I calculated, it is a weak positive correlation. Got it? Make sense? Now, let's look at a different data set. Here's another data set. Move this over here. With height and weight still, 10 cases. And if we put in this scatter plot, you can see that the trend line is in a more upward slope. See how that goes? And if we add the regression coefficient here, you see is a steady upward increase. And in this data, for every case, the shorter person was associated with a lower weight. See? A little bit taller, a little bit heavier, a little bit taller, a little bit heavier, a little bit taller, a little bit heavier. Each one makes this line just keep increasing. And if you look, all of the dots are right around the regression line. This shows that if I know somebody's height, I can predict their weight really accurately. And that is reflected in this number right here, which is the correlation coefficient of a super strong 0.968, blah, blah, blah. So that's how it works. The more strongly and consistently two variables are related to each other, the stronger the correlation is, the better the regression line predicts the actual dots, the actual data. So stronger correlations lead to stronger regression coefficients, and that means you're better able to predict values of y for each value of x. So that's how correlation and regression are related to each other.